All right, so now we're going to talk about adjoints of discrete Hamiltonians. And let me sort of just remind you that this comes from the definition of the adjoint. So if you're given a one-step method, okay, so phi h, for example, okay, then the adjoint is given by following. So you denote the adjoint by the star of it. So this is just going to be the negative, sort of that one-step method with a negative time step, and you take its inverse. Okay, so a method. Well, actually, we want to define the adjoint, right? So a method, one-step method, is symmetric, right, if it is self-adjoint, right, which basically means that it is its own adjoint. Okay, and in particular, all exact time h flow maps, it's like of continuous dynamical systems are self-adjoint and hence symmetric. So if we recall, it's like in the case of the discrete Lagrangians, you can write down the adjoint of the Hamiltonian map, discrete Hamiltonian map associated with or generated by the discrete Lagrangian in terms of another discrete Lagrangian, which we call the adjoint discrete Lagrangian. So in sort of discrete Hamiltonian mechanics, if you will, in discrete Lagrangian mechanics, right, if you recall, you can write down a adjoint discrete Lagrangian, LD star, Q0, Q1, which depends on H, and that's given by minus LD Q1, Q0 with a minus H here. Okay, so that's basically what happens. Okay, and so it's natural to ask whether in the context of discrete Hamiltonian mechanics, we can say something similar about discrete Hamiltonians. Okay, so one thing to observe, of course, is that when you write this, right, you have this swap. It's like of the arguments, if you will. Okay, so there immediately it's like one potentially is a problem, because in the type 1 generating functions, it's like, the arguments are both of the same type, right? They're both position variables. But that's not true of the type 2 and type 3 generating functions, which are the basis for discrete Hamiltonian mechanics, because one's a position variable and one's a momentum variable. So if you swap the order, then you don't have the same type of generating function, right? You swap the order of the variables in the type 1 generating function, they're still both position variables. You could at least imagine evaluating them on the type 1 generating function. So that's not true with again, a sort of discrete Hamiltonians. Okay, so what that sort of suggests to you is that when you take adjoints, so when taking adjoints of discrete Hamiltonians, right, you have to change the type of the generating function. Okay, so that's one thing. And then the next thing you have to think about is that, well, if you change the type, what does it really mean to be self-adjoint? Okay. All right, so let me first define for you this notion of adjoint in terms of type 2 and type 3 generating functions. Okay, so the adjoint of a discrete Hamiltonian is given by the following. Okay, So, okay, so I have HD plus, right? HD plus normally depends on initial position, final momentum, okay? But the adjoint of it is going to be a different type of generating function, which depends on the initial momentum and the final position. Okay, so I'm going to write this as P0, Q1, initial position, final momentum, all right, and a time step h. And then this is equal to minus HD plus Q1 P0 minus h. Okay, so again, observe that what this is basically saying is that HD if plus star is a different type of generating function than HD plus. Okay, and the same thing is true of HD minus star. Okay, as you might imagine, is the other type of generating function. So it's given by initial position, final momentum. Okay, and then this is expressed in terms of minus HD minus P1 Q0 with a minus h. Okay. All right. So that's how you define the adjoint of a discrete Hamiltonian. But now you still have a problem, right? Because now it's like you've changed the type of the generating function when taking the adjoint. So what does it really mean to have a discrete Hamiltonian which is self-adjoint? Okay. All right. So the way you do this is the following. So you observe the following fact that if you have a generating function of a particular type which generates a symplectic map, you can use what is called, you can take the Legendre transform of that generating function to give you a different type of generating function which generates the same symplectic map. Okay, so what you basically need to do is you need to do two things, right? So on the one hand, you have a different type of generating, the adjoint is the different type of generating function, which is constructed in a prescribed way from the original discrete Hamiltonian. But you can also take the Legendre transform of the original discrete Hamiltonian to give you a generating function of the same type as the adjoint. And so then you can do a comparison there. Okay? So, so what you do, if you will, is you need to do that kind of comparison. And then the other thing it's like one can observe is that like is true. It's like in the usual case, the adjoint of the adjoint of the discrete Hamiltonian is the discrete Hamiltonian itself, right? Okay, so that's one observation. So okay, so so the HD plus and minus you should think of as being giving you the same. Well, it's giving you the same symplectic map, but represented in terms of different types of generating functions. Okay. So you can sort of say the definition is the following. Okay. So a sort of type 2 or 3 generating function is self-adjoint. Okay. Okay, if it is equal up to equivalency. So again, it's like generating functions have this sort of non-uniqueness, if you will. It's like where if you sort of, for example, add a constant to a generating function, it doesn't change the symplectic map it generates. So there is some non-uniqueness. It's like in how generating functions relate to symplectic maps. So when we talk about equality, we really talk about equality in the sense of the symplectic map it generates. Okay, all right. So this is self-adjoint if it's equal up to equivalency to the Legendre transform of its adjoint. Okay, so basically what happening, if you will, is that if, for example, you started with a, it's like one of these generating functions which depend on, which normally depends on initial position and final momentum, right? You can construct a different type of generating function by taking its Legendre transform. Okay, so you can sort of do two things. You can either say, well, okay, I first take its adjoint, which switches the type of generating function which I'm working with, and then I can take the Legendre transform of the adjoint, and that sort of switches back to the original type of generating function, which I can then compare with this HD. Okay, so that's basically what I want to do. Okay, so and you can check that the two generating functions are related in the following way. So HD minus, say, pk qk plus 1 h, right, is equal to minus pk qk minus pk plus 1 qk plus 1 plus hd plus qk pk plus 1, which depends on h. Okay, so this is the Legendre transform, which relates two different types of generating functions, which both generate the same symplectic map. Okay, so what you want to do then is, if you had HD, right, plus, okay, say QK PK plus 1, and then you take its adjoint, HD plus adjoint, right, then this is the different type of generating function, and so you have to take the Legendre transform of this. Okay, so you have to have basically something like this plus pk qk plus pk plus 1 qk plus 1. Okay, and then you have to ask whether this is equal to this. Okay. All right, so that's basically what has to happen, right? If you want to check for self-adjointness, right? So to check for self-adjointness, right? You do the following: you take a generating function, you take its adjoint, and then you Legendre transform it so that it's the correct type of generating function. Okay. All right, so that's more or less what has to happen. And then what's always understood, it's like when you write something like this down, is that you extremize over the values which are not prescribed. It's like on the left-hand side, right? So you extremize this over pk and qk plus 1, if you will. Okay, so that's basically what you have to do. Okay, so you can ask whether the original generating function, right, is equal to taking the adjoint, shifting it by this Legendre transform, and then extremizing over the terms which don't show up on the left. If that thing is equivalent to this, then you say that this HD plus is self-adjoint. Okay, so it's a little bit more involved, but that's sort of really just a consequence of the fact that you're dealing with these type of generating functions, which it's like are somehow asymmetric in the sense that they don't specify both the positions at the initial and final point, or both the momentums at the initial and final point, right? So the type 2 and type 3 generating functions, it's like have this kind of mixed kind of boundary condition property. Okay, but anyhow, so this gives you, it's like the appropriate notion of self-adjointness. Then once you have this notion of self-adjointness, then the usual kind of results about, integrators which are symmetric, having even order, all those kind of things persist in the obvious way. And then I think the other thing which is worth observing is that, it's like all the usual kind of variational error analysis, which says that you can analyze the order of accuracy of the method in terms of the discrete Hamiltonian, and its ability to approximate the exact discrete Hamiltonian. All those kind of things, again, persist at the Hamiltonian level as well. Okay, so let me just stop here for now.